plot slice and DC?
I started a small pull request to fix some plot utilities, but that's a very small one. So
Okay.
Nothing really new.
Okay.
I've pushed the whole tile inversions, and now the bottleneck is the misfit the combo objective function. You need to parallelize that part. So we just need to talk about like where you think we should or how we should implement it.
Okay, that should actually be hopefully pretty straightforward.
Yeah.
Okay, sorry. So you're just saying there's a few things to go over. So SEG stuff. Dieter sent along some cool plotting utility code. So I'll demo that, and I think it he's got the pull request ready, so I think it's almost ready to go. We're hoping that you might be game to talk a little bit about the DC, even just a high level overview, and we can go deeper next week.
Yeah, sure. Start preparing now.
Yeah, exactly. I put it in the email, so. Yeah, no worries. And then objective function stuff. Okay, so that gives us 4 things. Anything else to add to the list?
I've pushed some ensemble stacking.
Okay.
It's more like pieces right now. It's not really something finished. I want to do a stack so that it looks at all the stacks and throws out one.
Yeah.
Or throws out the ones that are not good. And then I got some MT stuff. I'm looking at the continuous waveform or continuous wavelet transform. For getting out lightning strikes and stuff like that. Yeah. My colleague did his PhD on stuff like that, so we've been going back and forth. So I kind of went down that rabbit hole. Didn't complete anything yet there, but I'm starting with throwing that into the process.
Okay.
But do you have a general MT processing like that? That seems like
I mean, the FFT we've been doing.
Oh, cool.
It's just to do pretty much, I guess, if I had a remote, start incorporating that. So yeah, all the basic things are there. It's just
nice.
Nothing finished yet because I got onto this inversion stuff. Process. Yeah.
That's fair.
So maybe in a couple weeks.
Okay, cool. That sounds good. Cool. Okay, well, let's maybe start with SEG stuff. And Thibaut, you were there for the whole thing. So I'll let you.
SEG was good, and I think it was really not really surprising, but it was really good. A lot of people, at least on the mining side of SEG, were aware of SimPEG or were looking at it more seriously, or are actually just using it. So it was actually I think we deserve a bit of self-congratulation at this one, because I feel we're much closer to a critical mass for the swing of the project than I thought we were at the beginning.
Yes. Who's actually using it?
We're not getting it. We had a good talk with people from Matrix, we have Diaz, so at least 2 just individual consultants that were well, now I'm thinking I'm not using it that often, but when there is a small portion of simulation and forward modeling, I'm using SimPEG because I don't have the workload to buy a very expensive software, but they're if I have to do some of this job, it's not a dead end. He does it. So from the academic group, so Aline, she did a PhD with Iago, and she's a professor now in Brazil, and she's using the GPG and start looking at SimPEG too, and to involve a future student. Jajas, who is moving towards more cross-gradient structural inversion, but he wants his student to use SimPEG for that. So we might have students developing structural inversion in SimPEG soon. So, Deepon was there.
Is he actually using it, or?
He's gonna do. They just started this semester, so they're still very early in the graduate studies. That's their plan.
On the biometric side of things, they have actually seriously heavily used SimPEG, and they've gone in and they've got their own sort of internal branch right now where they've gone in and made a whole bunch of modifications, done some work in terms of speed up. And so I had a really good chat with their new CTO, And so I'm going to follow up with him. He seemed quite receptive to at least having a conversation about what they did and where they wanted to know the biggest improvements and things like that. I don't know if they'll contribute directly, and that's probably okay because we might want to sort of do it differently. But if we can learn from what they did and not go down the same rabbit holes that they did and all that sort of thing, that would be huge.
Yeah, they could just flag it.
That would be nice. Yeah. Otherwise, it's a bit kind of off. They can, well, at least somehow contribute back.
Yeah.
They don't really necessary to write things, but even point out where have to change what was the bottom.
And I think there's actually a fair bit of motivation for them to do that because I told them that we're going to be working on improvements and all of that sort of stuff and some structural changes. And so, like, if they're off on their own private branch, it's going to get left
That's
behind.
fun, right?
Yeah. So I think there's actually some pretty significant motivation for them to sort of stay tied into the ecosystem, which is really cool. And then I had also a good chat with Nestor, who I worked with when I was at Schlumberger that first summer. He's been doing a whole bunch of casing stuff, and he is very much like a mathematical physicist. So he likes to derive things and do all the integrals in the complex plane and all that sort of stuff. And so he's got a solution that he wants to actually test out against SimPEG for anisotropic backgrounds. So we'll be in touch with him on that, which is kind of cool. So it would be nice because it's like a completely independently developed approach for understanding what's going on. So that's kind of cool. And what about the hackathon?
Oh yeah, just to finish on that note, I was thinking I'm that close to convince Peter Leliev to move from Fortran to Python. Yeah, no, he was like, yeah, like explain to me more. Like we had a really long, in-depth conversation, and he was like, yeah, I thought like Fortran would be the way to go for that, but seems like you were down that path yet, and Python is maybe a bit more friendly, so I should check that out. Maybe I'm gonna convert. So that would be a good contributor.
Peter was the reviewer of the SimPEG first SimPEG paper.
Yeah,
it was pretty. I think on my end, I think I was a little bit pessimistic about why not? Oh, he was positive, but not like on that Python.
Yeah, so he might have review his own review. Like
what's his status? What is
he's still a researcher at Memorial. Like they are in between funding at the moment, but yeah, so he's still there. The hackathon, so there was 2 hackathons, and I only did one. So like there was the Agile hackathon on the first before the conference Saturday, Sunday. It was fun. I mean, I was the only non-seismic person, and it was like about a group of 30 people, and it was not like a hackathon like, okay, we're gonna give you some problems, you make some team, and you're gonna try to solve it. Like for most of them, actually, was like, I mean, among the 30 people, there were at least 20 that were the actual developer of the DBito package, which is a symbolic finite difference for seismic.
That's actually it's like a was that COMSOL? Like you write down the equations and can design the mesh and put a boundary conditions and stuff like that.
Yeah, it's kind of like that. Like it's literally you write your PDE, you write your boundary condition, but like you literally write derivative, blah blah blah, etc. And then you solve equation plus boundary condition. So the syntax was actually nice.
What was their motivation? Because there's is it a FinePy? It's a similar package for finding volume. What was their a sort of motivation, and what's their kind of
I didn't know about FinePy before you just mentioned it, so I don't know. I'm not gonna compare with it, but like the motivation is that they're doing everything in symbolic, and that gives them actually a lot of freedom on how to design each derivative, etc. They can literally say, "Oh, I want a derivative of order 9," and they got it. And I think the real motivation behind that is also that they want hypercritical. It's pretty much like one of the things that they want. Like it's not uncommon for them to use a 21-point gradient tensor. Like it's actually almost a norm. Like it's like we use like the default is a 21 gradient 21 stem cell gradient. So, which is
Do they have sensitivities, or it's all forward modeling?
they have, I did not touch really the inversion, but they have like the inversion as part of that. But I did not look at that.
That's very specific to seismic, right? This package is very specific to seismic.
Not really specific, but really like all the example and everything done with that is seismic. I did the first non-seismic stuff with it. That was like I did. I plugged a portion of SimPEG, we wrote a portion of it, and just solved the software modeling with DVTO instead of discretize.
Okay.
So that was kind of my project, because like as I was saying, like they were not like a specific project, but like 20 people were there. So like, but there were people from Imperial College London, people from Brazil, people from Felix Group. So it was actually one of the first, and they usually work all together to develop that. But that was actually the very first time that most of them were sitting in the same room. So they just continued their own project, but in the same room. But like they were like way down the path. So it's like so. Actually, they were working on still parallelization. Like DVTO is highly parallelized. That's also one of the things. Like they do evolution symbolic, and it's heavily parallelized, meaning that so obviously each source for seismic, each source is parallelized, but then so they separate by source, but after that for each source there is a parallelization inside the difference. So like they have like these two levels of parallelization. Yeah. So actually, they were doing a workshop demonstration, that was demonstrating the DVTO's power, and they were running 1,600 seismic source on 34,000 core.
Wow.
that was their workshop.
I'm impressed they have that much core.
Yeah. All they do in the cloud.
They did that on Google Cloud.
I wonder how much that runs.
Yeah. How much did it cost?
I don't know, but actually doing it the inversion was taking 10 minutes.
Okay.
So like you don't need it for that long. But I don't know. I have no idea.
Was that 3D? I think I'm sure
it was only 2D for that one. But yeah, so that was my project with DVTO. Just like okay, like a lot of people are way down the path. So I was just like, okay, I'm just gonna look at this package and see the good if I get it. And actually, the symbolic writing was actually nice. And for them, I was like, okay, that's the first time somebody used it for doing seismic, and they also realized like they write all the PD like more like in a scalar way, while we use gradient, divergent, curl, etc. And for them, that was a big takeout. Oh. We don't have the gradient or the divergent or the curl in that thing, and so it became some sort of a priority on for them. Like, okay, we need this vector operator, not only doing scalar.
So Felix Group is one of the part, like they're actually working on it.
Who's that?
The Felix Group is working.
Yes, so they Matthias and Philippe were the biggest contributor from Felix Group, and basically, what they did also, they wrote like a Julia wrapper, but when they do discretization in Julia, they actually call DVTO, which is in Python.
Yeah, I remember Matthias was working on Python, and I think that's probably the extension of that.
So
I think then they probably have like a version component.
Oh yeah, no, they have it. I did not. I just look at the package, show how it was written, how they deal with symbolic, and after that plug that to do the DC forward, and I was done. I didn't go too much deeper because I mean the idea was not to replace this, but I was just like look at what were the good ideas for that.
Hey Thibault, was there anybody in Felix's group? Is there anybody there that's using SimPEG?
No.
Because you said they're programming Python, right?
Like they have they have this DVTO package, which is their finite difference package. After that, I'm not sure. Like I know they have also a good portion of Julia, but yeah, they're entirely toward like seismic. So I'm not like they are not looking at SimPEG at all at the moment.
Okay.
Yeah, we don't really have many seismic examples, so until we sort of get some of those, it's not surprising that they're not really aware of it. or I mean, I'm sure they're slightly aware of it, but not that it could be used for seismic.
No, I was just thinking if they were kind of at least philosophically on board, they might actually want to just contribute almost from scratch, just try to develop something.
Yeah, yeah, that could be something potentially worth following up on if there was context there.
Solvers.
Yeah. Okay. Any other questions about SEG or?
Talk with success.
No. No, not at all.
Really? There's not that many people that showed up.
Not many people and a lot of technical difficulties. Like I'm not impressed by the SEG organization. And
oh really?
No, that was like many people got many problems on that talk. No, that was not okay.
Oh wow, okay.
I mean, like this workshop I talk about, like about cloud. It's a workshop, full afternoon about cloud computing. They never got internet. They never got internet. They had to use somebody's phone as a hotspot to get internet. Like the SEG was not able to provide in the convention standard was not able to provide them with internet, and they asked it months in advance just to find out when they arrive in the room to prepare that. Where is the internet? What?
Really?
No, like Felix was pissed.
How come there's no internet?
No, that's the level of organization the SEG provided us. So many victims.
Well, you got a trip right now.
Yeah.
All right.
Shows the political.
So let's switch gears. I'm gonna share my screen here, Doug. So just let me know if you can see this. Does that work?
Yeah.
Okay, excellent. So this is code from Dieter. So he's been exploring SimPEG for marine CSEM. So I sent him a 3D, just a simple forward simulation with a single source and some receivers. And he's run some comparisons with EMPyMod. And for the very simple example with very coarse discretization, we're still in decent agreement. So like, obviously there's lots that can be done in terms of making sure we're evaluating on, edges and things like that for electric fields. And there's stuff to improve there. But overall, it's nice to see that our forward 3D simulation agrees with a independently developed 1D forward simulation that takes a different approach. And so this is something that he's worked on for, I forget where he first implemented this, but the idea is that we can have interactive plots for scrolling through models. So this is just implemented on the tensor mesh. I meant to look for the octree. I forget where we're at for plotting in the octree.
I think it's good.
So then this should plug directly into the octree as well.
There's only missing color matching.
Oh, okay. Cool. So this, we're gonna look at Craig's inversion results. Dieter introduced me to shelves, so this is something I want to look into. I guess it's like a new iteration on Pickle. So it's something just to check out. I don't actually know how it works yet. So this is the slicer. So it's a method on the mesh class. This is the tensor mesh. And the LP out, that's just the model. So that's the inversion model. So we have a depth slice and then two cross sections. And so as I scroll.
That's a wheel scroll?
Yeah, that's a wheel scroll. So that actually moves the depth. So that's when I'm scrolling over this guy. If I scroll over this guy, you can see the lines moving, right?
Oh, that's sweet.
So that changes where that is. And then also all of the zooming is linked. So I can zoom in here.
Oh, great. And then you have the coordinate points on the...
Yeah.
That's cool.
So it's pretty slick. So that's sort of the standard. And then he's gone in and there's a few other things that you can set. So here he's set where the initial slices are. And then he's also set bounds for where it's transparent.
That's cool.
Okay.
And then all of the P color options are also hooked up. So if you want to plot the mesh on top or use like a log norm in a different color scale, that is all in there.
Wow.
And then here, this is also just giving you an idea of how the slicer is working. So if instead of calling it as a method on the mesh class, you just want to construct it, you can do that. So here he creates this tracker from the slicer, which is what is being called under the hood, with the mesh and the output or the model. And then here, it's just the matplotlib tracker that you have to connect to the scroll bar. So you could probably connect it to arrows or whatever else if you want to change how you're interacting with this.
Can you go all the way top? Is that what kind of platform? Oh, is that just Matplotlib?
It's just Matplotlib.
Notebook.
Yeah.
Is that going to work in inline? Matplotlib inline, is that going to work?
I do not know. Probably not.
It's curious.
I mean, it should plot, but I don't know if it'll be interactive.
I know it's
Yeah, it's not going to be interactive.
Still, that means we can
But that's
use
good.
just the fixed parameters.
Yeah, that's a
Yeah.
parameter. So I can set the slicers and yeah, cool. That's nice.
Yeah.
That's really nice.
Yeah, so he's got a pull request. You can check it out. I think it's like basically ready to go. We can maybe just convert. We can maybe just convert this example into, like this notebook into an example.
Yeah. Let's
but-
test it on tree mesh too, right?
Yeah, because I think it might just work. It's not obviously hooked up to the tree mesh yet, but if we use this and try it on a tree mesh example, we can see if that works.
I'm just going to do it a bit slower, I think, because Joe's doing a bunch of projections on that.
Yeah, we can probably also provide, this is something that I've done inside the plot slice, and we might want to expose it slightly higher up, bounds on where you're actually plotting. Because I found for the casing stuff, for example, like if my padding is so far and then my finest cells are like millimeters. So it was trying to project down trying to project 30 kilometers of plotting down to millimeter scale and crashed, not surprisingly. So put the bounds in and then that works.
Would that be part of the zoom function? Or?
We could get that fancy. For the first pass, I would just stick it on the outside. And just say like, this is the range I'm interested in looking at.
Yeah.
We probably could do it dynamically at some point, but yeah, to sort of get us through, that would be the first thing.
Just a quick comment, when you zoom, should we make sure that the axis equal stays the same, because when you did the zoom in, it stretched the image, right?
That is true.
Which is a little bit tricky.
A little bit deceiving. It might be tricky to dynamically resize the plot, but we can try. Because like when we do stuff with interact, for example, we're actually redrawing the figure like with the slide bars. Here, I don't believe that's what's actually happening.
Okay.
So there would have to be like an event handler, basically, that watches if you zoom and then changes scales.
That's amazing.
Yeah.
That's super cool.
I mean, I'm most excited for Arctree because we had such a hard time plotting with finding ways to show the results on Arctree.
Yeah. Well, and I think this is just such a nice way to actually view your 3D model like pretty quickly and easily. So very excited about that.
You guys are happy with the side view? Some people are. I'm cool with it, but
yeah,
I'm fine.
Yeah.
I think that looks great.
Yeah.
Side views. How did you change where the cross sections are?
Just scrolling. So if I mouse over this, well, it's not live, sorry. So if I mouse over this and I'm just scrolling with my scroll bar,
okay.
That changes whatever panel my mouse is active on. So if I'm on this one right here, the big one, it's going to change my Z index.
Oh, nice. Okay.
Yeah.
That's really nice.
Yeah.
Imagine for apps, You know, this is reducing the number of buttons that we have to put up.
Yeah.
Now it's just a matter of putting it up. That's great.
Yeah.
But that's sort of like that's more interactive apps, I guess. But like that kind of, it's hard to in Jupyter Wi-Fi widget like that types of interaction. I think Matplotlib seems like providing that, which is nice.
Yeah. So thanks to Dieter for that. We'll get an example built and then get that pull request in pretty quickly. But if you do want to check it out, it's on the Slicer branch, I believe it's called. So it's this one here, initial Slicer commit. And then the branch here is just called Slicer. So that's that. The other, I can give just a very quick overview of some things that are coming in. So in SimPEG, there's a few pull requests on the go, and I actually would appreciate if people could take a quick look back at some of these pull requests that have been open for quite a while. And if the changes are still relevant, there's a lot of merge conflicts and things like that. So just go through that. If not, then you can just close the pull request. There's some that I think have been surpassed by developments elsewhere, but I don't have the picture of that to know. One that I'm working on, and I'll go through and make a few more comments before I jump in and ask people for review. But I added electric field data to the DC problem, because when I was comparing, or like for my thesis, I was thinking both about DC and EM. So like it's just easier to look at electric field data all the way through. So I added those derivatives. I also added charge density throughout, because when you're actually plotting, like charge depends on the size of your mesh. And so you don't actually want to necessarily be showing that in all cases. So charge density. I added for the directives, just for the ones where we're saving models and outputs, I added the option to actually like save it into a directory rather than your current working directory. So you can change, like, because the one thing that I found is that if I had 4 notebooks, each running in versions, then you just get like a whole ton of models in there and it's confusing. So if you want to just put it in a folder underneath that, you can. There'll be some of the parametric map stuff coming in. So the new implementation of the block that like you can change to an ellipsoid kind of thing.
Oh yeah.
I'll create an example of that. And then what else? Oh, and then this also includes the sum map and the homogeneous map.
Oh,
like
really?
a slight rewrite of that. So I'll get you to take a look at that whenever you have a chance.
Do you have an example for this, or you want me to bring one in? Or?
If you have an example, that'd be awesome. I created some tests so you can sort of look at that. Yeah. But I'm also happy to bring one in if you don't have one handy. Cool. Are there any other quick pull requests? Do you want to go over the objective functions stuff real quick?
Well, the big one here is the PF, right? You commented on it and never went through your comments, so that's kind of what the status of this. But
that's this one.
Yeah.
Okay.
And I would like to add an example for amplitude inversion, because we have the functionality, but we don't have an example for it. No, we can finish this one.
Okay.
Yeah.
Cool.
What you're asking for? Oh, the tile. I don't have a PR.
That's fine.
Yeah. Can you bring the combo objective function? Just the code.
Just the code.
Objective function. Yeah. Go down to combo. So when we're going to do when we're doing tile inversion, we're just stacking a bunch of misfit functions.
Mm-hmm.
If you go to combo, oh,
Oh,
Oh, yeah,
there it
there
is.
you go.
Yeah.
When we evaluate, can you just go down slightly?
Mm-hmm.
Validation. Yeah, the call. So this loop here, this could become like, as many data points as you have. So we should parallelize this chunk.
Yeah, that as well as the same thing for the
derivatives,
derivative and the
right.
derivative.
Yeah.
Yeah, absolutely.
And so I was thinking for now, we could just do multiprocessing, but I don't know if you want to talk about Dask or.
So I think the question there is like, is that like really independent loop, or like there's a lot of other connections going on?
It actually should be independent at this stage.
Shared memory, right? You're stacking a vector on each other on itself,
but you can evaluate all of them
Yeah,
independently
yeah,
and some afterwards.
that's
So it is actually truly an independent loop. This is exactly where we want the first level of parallelization in SimPEG.
Well, if that's the case, that's really simple.
Yeah. I think Dask, and I was wondering if you might.
Yeah, I could show you a little bit of what I was just playing with.
Yeah.
It's very like juvenile, but I think that's actually enough to do this types of stuff.
Yeah. Do you want to show
sure.
us that? Is that okay? Can you just maybe join the Hangout?
How did you?
I posted it on Slack. It should be on general and meetings.
So this is sort of the set. Is it? Okay, let's see. Yeah. So you can put that's the initiation of the client or whatever workers. So you can import Dask. I think actually if you just install Conda, it's a base package, so it's already probably installed, so you can run it. And then you can put the number of workers. So I have 4 cores, so you can put 4. And then you can also set like a number of thread per workers, because sometimes it's a bottleneck. If you think about the PyMet solver or Perdiso, it actually uses the maximum threads. So you need to be careful when you're like parallelizing, because let's say you're going to solve a bunch of DC problem. If you don't set the number of thread right, it'll try to run like, I don't know, a lot of threads. So it's actually the same problem for you're running the UBC code. You need to be careful about like setting the thread when you're doing parallelization. Anyway, so that's how it looks like. And then it'll show you, okay, what's the system you look like. And what's actually nice about here, you can click this guy. And you can see sort of it does the profiling.
Oh.
Which is actually nice. So you can actually kind of check how you're doing it. And this is sort of a simple example. I'm thinking about like a parallelizing DC problem. So the idea, so this argument here is the input. It's very simple. So why not so I'm thinking about multiple lines. Like let's say I got 5 lines. I want to parallelize that. And then each line doesn't, like I don't need any kind of conversation with each line. So it's completely separate. Mm-hmm. So it's what they call embarrassingly parallelized problem, which is like the simplest case. So if you take, like you see the function looks like, so it takes the survey function. So what it does, it takes the parameters and choose dipole, whatever, it generates the survey. So by changing the y naught, it'll change the location of the line. And then I got the mesh function. So this is the like what the dumb wrote. This is mesh builder for Octree code. And then, yeah, I'm not going to go to the details, but I think you need to refine in multiple steps. So I think this is sort of the optimized parameter that I found for working for DC. Anyway, so then generate the problem. of DC. I've got mapping problem, and then genetic synthetic data. And after that, I want to stack it, right? So I want to run in parallel, and then stack it later. So that's how it looks like. Let's say I got 20 lines. And this is actually, there are multiple ways, but I think this is actually the simplest way, and that's actually very similar to multiprocessing. So what it does actually, client.map. So that's like, it's actually mapping your function to all the workers. So, okay, I got DC simulation, and I need to put the inputs. So input can be arrays or whatever, so, but you need to kind of make it multiple. So I'm just making a tuple, which is my arguments. If you look at the function inside, so arguments is a tuple that I'm outputting as a y0 and p0. p0 is nothing, I was just playing with it. Then this is actually the important step. So futures doesn't do anything, but we're just gonna run. So it's actually fast, it's not done yet. So what future does, it actually generates all the trees, what it's supposed to, it plans. So it doesn't, like, that's why it's called future. So in the future, we're gonna do something, but it's not done yet. This is actually an important step. If you have enough memory to load everything up to your memory, then that's what it does. Persist actually use all the things into the memory. Otherwise, I think I'm not exactly sure what's happening, but it wants to be memory efficient. So you're gonna lose your speed, which you may not want to do. So I think most of our cases, I think that's what you want to do. Because I think it's not that much big memory, but we're loading up. And this is where actual computation happens. So yeah, so I think this one doesn't do anything, right? But that's actually where things are happening. So it ran. So it actually ran 20 simulation of DC data, and that's done now.
Created the meshes too, right? You created the meshes.
Created a mesh, run. So that could be really fast. So I think this wasn't a big example, but if you look, this is actually like fair geometry. So 50-meter spacing, I got end spacing 10, line length was kilometer. So I think it's not a really tiny data set, but still okay, kind of toy example. But that's sort of the speed that you can get. Which is actually nice. So I think it's almost linear. I think it's in theory it's a linearly scaled, right? There's no talking, right?
Yeah.
So yeah, I think that's mostly what we need, and I think this is actually fine. So I was kind of playing with how it does. Is it comparable with multiprocessing? It does. So I think I was actually doing it.
And is there an example that you used to base this off of, or how did you?
Oh, maybe that was a bit deceiving. Not exactly sure what happened. But it was supposed to be similar. I think it was a bit too fast. Maybe for a fair comparison, I think I had to run all three things together. I guess not exactly sure what it is. And so that's sort of like how simple it is. So this is using multiprocessing, and if you look at that, that's pull.map, put a function, put arguments, and in a list, and loop over. So that's actually pretty simple, and I could show you how I'm doing it in SimPEG EM1D, for instance. So that's how it looks like. So I actually implemented Desk. I got an option for either use Desk or multiprocessing. So what it does, I got a client here, just initiating. And I think there's probably a better way later. I think we can store that client in a class and then kind of play with it. But this is a sort of simplest. I don't care. I don't want to change whole bunch of other parts of my code, and I know this is actually where I need the parallelization, then yeah, that's it. So you just need to have a run simulation and generate a function like that can output the arguments, and then loop over and load it up to memory, gather it, get the result. That's it. So sensitivity is basically same in this case. So if you have a function, like this is actually assuming when you're generating the sensitivity. So we got a small enough problem. Then do the same thing, have a function, run simulation. For me, it does actually both forward and sensitivity computation. So like, yeah, it's basically same. Then you store that into a matrix. So yeah, I think so. Like kind of parallelizing that loop is actually really simple. If you don't have any conversations, and
Yeah.
That's something that I wasn't sure. So.
And Sagi, was there an example, or where did you find out about?
Oh, so there's if you go to Dask, there's a binder.
Oh, okay.
And like that tutorial is actually great.
Excellent.
So like if you just I think there are 3 or 4.
Yeah.
Yeah, actually I just did it on last weekend. I was kind of curious.
Yeah.
But yeah, I kind of played a little bit, but.
Did you play around at all with the decorators? Because I know that you can do that for functions, which is kind of nice, because then you don't actually change really the code.
Yeah, you can do that.
Yeah.
So there's I think that's what they call lazy loading or lazy something.
Yeah.
So you can actually do a for loop.
Yeah.
To generate. So that map was more like a fewer lines.
Yeah.
But you can actually generate the for loop. So I think what in objective function, what you need to do, you just need to append.
Yeah.
So generate some sort of like a placeholder and then append that.
Yeah.
You're generating basically that future function. And then at the end of the loop, you run that. So that'll do a parallelization and run it.
Different syntax.
Yeah.
So after you've done this, can you get statistics on exactly how many nodes were used, how much time was spent in each, and just what the overall performance?
Yeah, so that's what you're seeing there. So
I can't really see that because it's really small.
So this is actually I ran 20 simulations. Can you see? Is that?
No, it's way too small. It's just in a.
Can you see that?
Is the Hangout full screen, Doug?
Oh, how do I do that?
If you go to the mouse over it and go to the top and click the green button. Or you can just stretch the window.
Oh, okay. Oh, there we go.
Yeah, so yeah, you can see that.
Yeah.
Yeah, so that example in the binder is actually nicer because they're using the Jupyter Lab, and then you can see the profiler on the side. So it's nicer. I think we can get that stuff set up maybe, but I don't know how to do it. Yeah,
that's the thing that's a bit missing about the processing is the timer. You'd like to know how far you are in your process, and now you just be able to see your.
Well, using the Dask is a big uptake because multiprocessing only work for a single cluster, for instance. But now you can scale up to big.
And Dask is a very well supported project. There's a lot of people invested in it. I mean, as you can tell by the fact that they've got beautiful
APIs.
Interfaces.
So I think in our SimPEG, there are a number of places actually we can put that either Dask or this stuff in, because usually matrix vector product, then if you got large matrix vector product, then that can be separated into a bunch of chunks. Assuming that's the a dense matrix, they don't support the sparse matrix product.
Well, but in that sense, though, the objective function is the first very high impact point in SimPEG, because then to do the DC inversion, for example, you could just create a different forward problem for each of those and add them up, and then that would do the same as what your sort of split up forward simulation.
Right. I think that's probably the level. I think in this case, because it's not quite proper for you've got lots of problems. Let's say you got 10,000 problem, 100,000 problem. I'm not sure parallelizing in that level is actually better.
I don't know what you're talking. What do you mean? Sorry.
Let's say you got an objective function, I'm not sure, if you got, let's say, 10,000 sources, and then I want to parallelize it for each of them.
Yeah.
And I don't want to have that as an objective function, I don't want to solve that as an each objective function.
Why not?
I don't know. And somehow there's always a little bit of a load for when you're generating objective function. I think I'm not sure how expensive that is. So I think that's probably better to parallelize in a problem level. In that case, so I think there's multiple.
Yeah.
Because I think this is actually a very simple case.
Yeah.
Right? But there could be pretty involved parallelization, but really tangled together. Then then I think there's kind of two levels. Okay, you got a problem, had a parallelization. Then at another level, okay, I'm going to do the joint inversion or whatever, multiple inversion. Then there's a level of very simple parallelization like this, have a different level, more abstract level of parallelization.
Yeah, but
Yes.
I do think that the objective function parallelization will get us 80%. We'll hit 80% of the cases that we're interested in right now. It's not going to hit parallelizing an airborne EM survey. That's fair. But the example that you just talked about, so if you've got 8 lines, that's a very easy level to do that at.
Yeah.
So
that's true.
Although it might not be exactly the same type of approach, this will get us 90% of the way with a very, very simple parallelization.
That's true. That's true.
And from what I understand, DAS kind of figures out before launching, figures out if there are multiple levels of parallelization and figures out sort of the best path forward. From what I understood from the talk, it kind of maps all the levels of parallelization and then it chunks up.
That's true.
Yeah, so starting there and then parallelizing, so for the EM code, then parallelizing over frequencies, for example, would be the next place that I would go. But I think that this, let's try and get it right at the objective function level first, and then it should be easy to propagate further inside, I think.
Yeah.
I'll look at it next week, this week, and then start again next week.
Yeah, that sounds good. Cool. That's really exciting, Sagi.
Mm-hmm.
Yeah, and what's exciting part is actually the octree code, because if you think about this is it's actually really simplifies things. I don't generating the mesh is actually pretty simple if you got the right functions and compared to tensor mesh. So yeah, it's actually more generic. Okay, I got a location of the survey. Then it'll figure it out. You just need to put the right arguments, but that's exciting part. And actually, we can have actually pretty small mesh compared to the previous case, which is kind of cool. So this is kind of an example of an octree code. So yeah, so that's actually the core part, how we're generating the mesh. And the plotting function works. Okay, maybe not. Yeah, so that's it's not a small mesh. So if you look at it, it's, but it's actually much smaller than tensor because you can go pretty coarse. I think what we need. It's actually, we just need a close, very small cells close to the electrodes and maybe a couple of the layers. Then after that, we're losing the resolution. So I think using coarse mesh, I think it's actually fine. And I think that's the most of the cases. So that we're up against it. Yeah, so I think this is kind of example. You can see the data, histogram. This is actually I haven't finished with your stuff, but anyway, this is we're generating the surface weight because it's a problem for DC using DUM's sparse inversion. That's sort of the result. Yeah, well, I kind of Anyway,
Working progress.
Point is working, and actually I play with DS data.
Confidential.
Confidential data.
Censoring this one.
This one, the guy's pretty cool.
So this is,
I heard the guys are pretty cool.
this is the DS data. That's actually kind of cool because it's actual 3D data. I've never really. This is actually the first time that I'm seeing first 3D, like a 3D data.
And distributed array, you mean?
Yeah. Oh, yeah. So that's the electrode location, and each electrode each source has like quite a bit of receivers. Not all the receivers, but quite a bit of receivers. And that's so we actually inverted the data. And it doesn't take that long if I'm using the octave code. So this is so far my best.
Yeah.
Not sure.
Is this one of the ones you sent last, or you?
No.
Since then? Okay.
I think this is actually where I'm using the surface weight.
Oh, okay. Oh, you look on this.
So if you look at the surface, it's actually not that bad.
Yeah.
It's pretty smooth. And I think that's the.
What are you doing for surface weights?
So surface weight is basically generating a large value for a couple of the layers, and then just putting that into the smoothness term. So by doing so, you're asking, okay, at this few layers, I really want to make it really smooth. So you're penalizing this like bumpy structures in this new surface. And that's actually the comparison with the other code. It's a REST 3D code.
Oh, okay, I was just gonna say, did you find that you still had to put a lot of what was the depth weighting?
No, I didn't.
Oh,
I'm not a big fan. It's a bit much because if you look at their structures, it's kind of like going down.
And this is our complaint, but people love it.
So that probably depends upon what they're looking for.
It's what you know. If they know that everything should be vertical, well, it's valid. But
well, I was just working on one too, and again, it just pulls it down. It makes everything look like a carrot. It's like there's no way that is right at depth. Like it can't be. But again, like the stuff near the surface and the top stuff, that's what the client liked, and they kind of don't really like the bottom. Like they just don't care about the bottom or something.
Anyway, so I think in a first order, they are like similar, but I think in that depth. We don't think any resolution. But anyway, so
can we benchmark? Can we do like a synthetic and send it both ways and then just figure out, where did they differ? Do you have access to Res 3D?
No.
Do you?
Yep.
Can we benchmark?
Could see why not.
That would be super useful for you, right? You want to know.
Well, the thing is we have. We have it because it's a preference of clients. Like Australians specifically love local. I don't know. That's what they use. And I guess so. We do have it, and it would be great to
try to send it to check. Let's just do a 3D problem, and
then. I could throw it on and run whatever you want. We are a little busy with the inversion machines right now, but I can do that for sure.
But what about using the example that you just have done? As far as the topography and the electrode layout, I mean, just keeps all of that infrastructure the same, except just change the model, put in a couple of things that you might think are geologically relevant, and just a simple model, and then run it through Res in 3D, and we could run it through here.
Yeah, that could definitely happen.
Because that wouldn't then take perhaps so much work on your part to generate something, because you've already got basically the survey set up, and then it also helps answer a couple of questions maybe with respect to what you're seeing, with all of this topography and with your particular survey.
Just swap the data.
So that's where we are.
That's nice, Soggy.
Cool. Well, that's exciting. Lots of good things on the go. Maybe next week we can, if everybody's playing around a bit with parallelization, that can maybe be the focus of the meeting, and try some things. We'll do a show and tell.
Sounds good.
Perfect.
Try some stuff over that desk. That's cool.
That'd be great. Doug, any other comments on your end?
No, that's great. I like Dieter's plotting, and Soggy, you guys did a nice job.
Excellent.
Bye, Dad.
See ya.
Wow.